Alright, this is going to be our first PowerPoints on sets and Venn diagrams. A lot of this is going to be a review, so I'm going to fly through it pretty quick. Feel free to pause, rewind, whatever you need to do as I move through it. Okay, so set notation. A set we've already kind of talked about is a collection of numbers or objects. The set of all digits, which we use to write numbers. So we might write 32, we might write 48, but the set of all digits that we use to write all numbers is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Notice that when we write sets that they're put inside brackets. And they are usually, each element of the set, each member of the set is separated by commas. We usually use capital letters to represent sets. So if we call V the set of all vowels, then V with a capital letter is equal to, notice the brackets, A, comma, E, comma, I, comma, O, comma, U. So all the elements are separated by commas. The numbers or objects in a set are called the elements or members of the set. We use the symbol, it's like an E, kind of a crooked E, or like a curved E more really, to mean is an element of, and we use that same E with a slash through it to mean is not an element of. So if we have the set A that has the elements 1, 2, 3, 4, 5, 6, 7, we can say that 4 is an element of A because it's right here. So it's obviously part of the set. It's a member of that set, so we call it an element of, and we write it this way. But 9 is not an element of A because 9 is not in set A. The set represented by a set of brackets with nothing inside, or the 0 with a line through it, is called the empty set, and it has no elements in it. So if we have set A equal to 2, 3, 5, 8, 13, 21, it has 6 elements, and the number of elements in a set we write this way. That means the number of things in set A. So if we count the things in set A, there's 1, 2, 3, 4, 5, 6. So the number of elements in set A is equal to 6. A set which has a finite, meaning a limited number, there's an end to how many there are. A finite set of elements is called a finite set. Set A that has the elements 2, 3, 5, 8, 13, 21 is a finite set. We can count the number of elements. We can write the number of elements in set A is equal to, and we can count them and write a number. 1, 2, 3, 4, 5, 6 is equal to 6. The empty set is also a finite set because the number of elements is 0. We can write down how many elements there are. Infinite sets, however, have infinitely many elements, and we can't write the number of elements in a set and give a number. It would just be infinity because there's an infinite number. And if we go back and we remember, this is the set of natural numbers. And that is an infinite set. This is the set of integers. And remember, that's an infinite set. Then this is the positive integers. This is the negative integers. This is our rational numbers. And that's an infinite set. And this is our real numbers, which is also an infinite set. So suppose P and Q are two sets. We have set P, we have set Q. P is a subset of Q if every element of P is also an element of Q. We can also think about this in English terms as P is inside Q. That means everything that's in P is also in Q. And we write subset using this symbol. It's like a sideways U with a line underneath it. So 2, 3, 5 is a subset of 1, 2, 3, 4, 5, 6 because 2 is inside this subset. 3 is inside this set, and 5 is inside this set, making this set a subset of this one. We say P is a proper subset of Q if P is a subset of Q but not equal to Q, meaning they don't have all of the same elements. This would also be a proper subset because every element in this set is not in this set. They're not equal. So every proper subset is also a subset. And we've gone over union and intersection before, so this should be a pretty quick review. If P and Q are two sets, then P with the upside down U is the intersection of P and Q. So that's all the elements that are in both P and Q. So if it's in both sets, then it's in the intersection. P union, which is just the regular U, is the union of P and Q and consists of all of the elements that are in one or the other. That means we're going to bring everything together. So if P is 1, 3, 4 and Q is the set 2, 3, 5, then the intersection is what's in both. So if we look, the element that's in both is 3. So P intersects Q is just the set that contains 3. The union, however, is we take everything in P, we take everything in Q, and we dump them together. We say here, we're just going to put it all together in this neat little bucket, and we're going to call that the union. So everything that's in P and everything that's in Q is in the union. And if it's in both, we only have to write it once in the union. So 1 goes in the union. 2 goes in the union. 3, we're only going to write it once, but it's in there. 4 goes in the union, and 5 goes in the union. So everything in both get dumped into that nice little bucket together. Two sets are disjoint or mutually exclusive if they have no intersection. They have no elements in common. So if there's no intersection, we call them disjoint or mutually exclusive. And an example of that would be all the letters in the alphabet in set A and all the integers, we'll put those in set B. Well, they have nothing in common because no letter is a number and no number is a letter. So we call these disjoint or mutually exclusive sets. So here's an example. We'll kind of look through it together. Part A says, true or false, 4 is an element of the set M. Well, here's the set M. So if we go up here and look, we have 2, 3, 5, 7, 8, and 9. 4 is not an element in there, so we're going to call that false. Then it says 6 is not an element of M. So we look up here, 2, 3, 5, 7, 8, 9. 6 is not in set M, so 6 is not an element of M. Therefore, that statement is true. Part B says list the sets. We're looking for the intersection of M and N. So we look up here, 2, there's no 2 in N. 3, there's 1. So 3 goes in the intersection because it's in both sets. So M intersects N contains the elements 3. 5 is not in N. 7 is not in N. 8 is not in N. 9 is in N. What about 4, 6, 10? So it's just 3, 9 that are in both sets. And then if we look at the intersection of those two sets, so the union, that's everything that's in both sets. So we have 2, 3, 4, 5, 6, 7, 8, 9, and 10. Everything that's in both of them, we're dumping them in the same set. Then it says, is M a subset of N? So is everything that's in M also in N? Is M inside N? No, because 2 here isn't over here. So that would be no. Then it says, is 9, 6, and 3 a subset of N? So what we want to know are 9, 6, and 3 all inside N? Well, there's the 9, there's the 6, and there's the 3. So the answer is yes. Okay, looking at set builder notation. You've seen this before. You probably didn't like it the first time you saw it, and you may not like it this time either. But set builder notation, this says set A, and then the brackets say the set of all. This little line means such that. So this is the set of all x, such that x is an integer. This tells us it's an integer. X is an element of the integers between -2 and 4, and we're including -2 and 4 because our sign is less than or equal to. So you can say the set of all x such that x is an integer between -2 and 4, including -2 and 4. You can also say the set of all x such that x is an integer greater than or equal to 2 and less than or equal to 4. Greater than or equal to 2, less than or equal to 4. Okay, so if we draw that on a number line, we have integers, so there's nothing in the middle. It's just all whole number integers, and it includes -2, -1, 0, 1, 2, 3, and 4. Those are all part of that set. So we say that A is a finite set, and the number of elements in set A, if we count them, 1, 2, 3, 4, 5, 6, 7, is equal to 7. Here's another example. This one reads, B is the set of all real numbers this time, because it says X is an element of the real numbers, such that X is greater than or equal to -2 and less than 4. We don't say less than or equal to because of our sign. So this one, since it's real numbers, it's not integers, so we're going to include everything in between the integers. So we start at -2, and we have a filled in circle because it's equal to, it includes -2. On the other end, because we're not including 4, it's less than 4, we're going to have an open circle. And then everything in between, we're going to shade because everything in between those two is included in that set. B is an infinite set. When we're talking about real numbers are an infinite set, and there are an infinite number of real numbers that are greater than or equal to -2 and less than 4. So we say that the number of elements in B is infinity. It's an infinite set. All right, last slide. Here's the example. Suppose set A is the set of all x such that x is greater than 3 and less than or equal to 10, and it is an integer. So when we write that in when we write it out in words, we would say the set of all, the set A, where are we at? Set A, and we're going to say that's all x such that x is greater than 3, all x such that x is greater than 3 or less than or equal to 10. Okay, so up here, let's add in the set A is all x that are elements of the integers. It has to be an integer. Such that x is greater than 3 or less than or equal to 10. Okay, so if they're integers, we're talking about whole numbers. Greater than 3, so we don't include 3. So if we were to write this set out as set notation instead of set builder notation, A would be the set where 3 is not included, but 4 is, 5, 6, 7, 8, 9, and we're going to include 10 because it's less than or equal to 10. So that's 4, 5, 6, 7, 8, 9, and 10. So those are the elements of set A. Now the number of elements in set A, all we do is count. 1, 2, 3, 4, 5, 6, 7. So the number of elements in set A is 7. You'll have a worksheet to work on with the sub. If you have any questions, you can always ask on Remind or Edmodo. It's going to be due on Tuesday. Please use your time wisely in class today, and y'all have a great weekend.